let's see here. Okay. We're recording. We're on board here. Okay, so just a couple of quick notes. I marked the tests. Means I don't have to lug them to Ottawa for the break. It was all self-serving anyways. You'll see I've stapled assignment 3 to the back. I just did completion, so if you handed it in, you got 100%. Great work. And it's just on the back. So make sure that it has a check mark on it, just on the front. And then just make sure that the mark is there on Moodle, just 1 out of 1. And then, of course, because I was doing these kind of fire drill style last night into the wee hours of the morning, maybe just check my adding. So how I work is I just subtract marks as I go. Okay, so assignment 3. Is for completion marks. And then check adding on test number 1. So if you have any questions about the marking or anything like that, then just let me know. I'll post the solution so you can have a look. There are 2 versions. There's a colon after the instructions. That's version 1. And then if there's no colon after instructions, that's version 2. Didn't really need to do it for you guys, but since I have 2 versions, I may as well use them. More in here. So just check the adding, more like check the subtracting. And if you have a higher mark than you should have, then don't tell me. How about that? Okay. Everyone got the chapter 4 notes? So today we're going to start chapter 4. Chapter 4 is kind of like, I think of them as training wheels. Okay, so we're going to keep going with these Z scores. And so we still use the Z table to find areas under the curve, but now we're going to change to talking about a mean observation, so an average observation instead of just a single observation. And so that's where we're starting in chapter 4. And then I call it kind of training wheels just because this is where we're going to introduce hypothesis testing and confidence intervals, which are going to haunt us for basically the rest of the term. Okay. What's nice about getting into this section, which is called inference in general, okay. Here, inference, is once we know the procedure for hypothesis testing, for example, then that procedure stays the same. And it just changes a little, the calculations change a little bit depending on the type of question that we have, right? And so we're going to lay the groundwork, kind of establish all these rules, these in and outs, and then we'll have that, and then we'll just introduce new types of problems that we can solve, right? But the framework stays the same. And so chapter 4 is going to feel very kind of crowded, I guess. Just because there's a lot of rules, a lot of procedure that we have to learn. But then when we have it, we'll know it, and it'll be ours. So inference is just a term, right? When we take, because this is what we said before, right? At the beginning of the term, we said, well, stats is going to be where we take sample information to say something about the whole population, right? Or what we could say is we take sample information to infer something about the population, right? So when we take sample information to infer something about the population. So that's inference, and there's going to be kind of two main streams of inference that we'll look at. We'll look at hypothesis testing and confidence intervals. And if you have a peek at your formula sheet, right, all those, the remaining formulas just outline a hypothesis test and a confidence interval for each of these different types of problems. Okay. So gonna zoom in here. I'll put some stuff up here for you to. So like I said, so far we've talked about a single observation, right? So the speed of a manatee, or the salary for a single person, right? So one individual is what I mean. Now we're gonna start talking about, okay, well, if we collect a sample, then usually we calculate the average, and then we want to use that average, that mean, to talk about the population mean, right? And so here in section 4.1 and also 4.2, we'll establish the distribution of the mean. Okay. And so we'll start here because this is kind of not that far-fetched. If x, and now we know this notation, we're comfortable with this notation, right? If x follows a normal distribution with a mean mu and a standard deviation sigma, right? So that's what we're used to seeing, right? So something follows a normal distribution, then the average, right, and the mean of that from that group is also going to follow a normal distribution with the same mean, right? Which kind of makes it should make sense, right? Because if a group has some population mean and then we sample from that group, then sample means, yeah, they should end up close around that population mean, right? And so we won't stray, so the mean won't change, but the standard deviation will change. Okay? The standard deviation is going to take the sigma score from a single observation and divide it by the square root of n, where n is the sample size. Right? So n is always going to be the sample size. And so what we have, right, is the only thing that really changes is that the standard deviation for a mean is really just the standard deviation over the square root of n. Gets messy when we're talking about standard deviation has a standard deviation in it. And so for that reason, this little chunk, sigma over root n, we call it the standard error instead. But it's essentially the standard deviation of the mean. And so this here, oops, guess I shouldn't. I did it again. This is the standard error. So what happens, right, is, well, to get a mean, x bar, right, we have to have a sample, right? We have to have a sample size. If you think about, well, what if I just have a sample of 1? Right? Then n would be 1. The square root of 1 is 1. Sigma over 1 is just sigma. So now you're back to this case, right? And so really, this is just a special case of this here, because the average of one value is just that value, right? And so what we could have done is we could have started here and said, well, a special case is when you have a sample size of 1, right? A single observation, then it has this distribution. Okay? But as you increase your sample size, that sigma over root n, because you're dividing by the square root of n, right? The square root of n, as n gets bigger and bigger and bigger, is going to get bigger and bigger and bigger, right? Just not as fast. Okay? But then the sigma getting divided by a number that keeps getting larger and larger is actually just going to get smaller and smaller, right? Think about, I don't know. I just like to pick numbers that I know how they behave, right? So think about if this was 4 and this was, if the square root of n was 2, right? Then 4 divided by 2 is 2, and then if sigma was 4 still, and the square root of n was, I don't know, 4, it would decrease, right, to 1. Lost track of what I wanted to say. So anyway, so that's an important concept, but it's also not that far-fetched, right? Because as we collect more and more of our population into our sample, right, we expect it to become more stable, right? And so here, my little note, we expect to see more variability, right? So more kind of fluctuation from sample to sample to sample. Right? And sample means from small sample sizes, and sample means from larger sample sizes. Okay? So as you increase your sample size, then that sigma over root n, right, the standard error is going to get smaller and smaller, meaning you've got a more stable kind of variation for your sample. Okay? Then I've got a note over here just saying that sigma over root n is the standard error, which we'll abbreviate SE. And as n increases, sigma over root n decreases. Oops. Any questions so far? Let's do this example. I'm going to add a page here. Call this example 1. The entrance exam for business schools, the GMAT, given to 100 students had a mean of 520 and a standard deviation of 120. Okay. So part A, what's the sampling distribution of the mean x bar? Okay. So we're given that the mean is 520. Oops. The standard deviation is 120, and the sample size that we have is 100. So part A is asking, what is the sampling distribution of the mean x bar? So the sampling distribution of the mean is on your formula sheet, right? And it's just the x bar follows a normal distribution with a mean mu and a standard deviation sigma over root n. So what you're going to do is you're just going to write that out and fill in the spots. Okay. So we've got X bar follows a normal distribution with a mean mu and a standard deviation sigma over root n. So in our case, we've got X bar follows a normal distribution with a mean of 520 and a standard deviation of 120 over the square root of 100. If you wanted to leave it like that, that's fine. I think that's probably what I would do. Or if you want to. Oh. Yes, indeed. 12. So, or X bar follows a normal distribution with a mean of 520 and a standard error of 12. Cool. Part B, what's the standard error for the mean of the sample of students? Just kind of reiterating. That the standard error is sigma over root n, which is just showing our 120 over the square root of 100, which we just calculated to be 12. So just showing that link, that this 12 is now the standard error. But if you want to, the standard error is just the standard deviation of the mean. Right? And so it gets a little confusing. So C, as the sample size increases, what happens to the standard error, assuming the standard deviation remains constant? We just talked about this, but in general, as n increases, I'll just make a note here, assuming sigma stays the same, sigma over root n decreases. Part D, if the sample size is doubled, what's the impact on the standard error? Finally, a real question. Wait, I thought you made these. Yeah, I stole them. If the sample size is doubled, what's the impact on the standard error? So now, say n is not 100, but 200. I'll just put in brackets doubled. Then what happens to sigma over root n? Sigma is still the 120 divided by the square root of 200 now. So 120 divided by that. So if we had to talk about the effect, right, we doubled our sample size, but we really only decreased our standard error by 2 units, right? And so doubling our sample size doesn't cut our standard error in half, right, just because of how square roots work, okay? So doubling our sample size results in, here we go. Oh, and you're in the back here, so can find you. in a decrease of 2 units in the standard error. Oh, really? Maybe I pressed something wrong. 120. So the square root of 200, I get 14.142. So. It is 2. Thank you, thank you. Not sure what happened. This calculator is not that awesome. 848528137.4. Is that what you got? Awesome. So not quite 2 units, but 12 minus that. Nice. Still not cutting it in half though. And still because of how square roots behave. Any questions about that? So what we're going to be doing, right, is, so we said we're going to collect a sample, we're going to calculate the sample mean, and then we want to infer stuff about that sample mean. And so, or use the sample mean to infer something about the population rather. And so, of course, we'll want to be able to calculate probabilities the same way that we did before, right? And so if we know that something follows a normal distribution, then we know that we can shrink it down to a z-score, right? And so now, instead of talking about z as x minus mu over sigma, right? Now we've got z, which is going to be x bar minus mu over sigma over root n, right? So it just gets a little bit bigger when we're talking about a mean observation, but we're still calculating a z-score. And then once we have that z-score, it behaves the same way that the other z-scores did, right? So once we have a z, we're back in familiar territory, right? And then we can use the z-table to calculate probabilities. So, just like I said, we can calculate probabilities associated with this mean observation instead of just a single observation. Let's do an example where we're using the z-score to find probabilities associated with a mean observation. Example 2. Let's see if I can. I don't think so. I'll add a page below here. You know what? Just so I don't have to scroll around so much. Repasting it so I have it. So suppose the mean weight of boxes shipped by a company is 12 kilos with a standard deviation of 4 kilos. Okay. Boxes are shipped in pallets of 10 boxes, and the shipper has a limit of 150 kilos for such shipments. Okay. And so we've got 10 boxes weighing an average of 12 kilos, right? But also this pallet overall can't weigh more than 150 kilos. Right? So let's see here. A, what's the probability that a pallet will exceed the limit of 150 kilos? And so we can rework this question, right? Because 150 kilos, if there's 10 boxes, that's really just saying, well, what's the probability that the mean of each of these boxes is more than 15 kilos, right? Because we've got 10 boxes. And so, part A, we've got something that looks like this. You can always just assume that you have a normal distribution, even if it doesn't say, and I'll talk about why in the next section. Okay? So I guess using it a little early, but it's okay. So we're told that we have a mean of 12 and a standard deviation of 4. Okay? And what we want to know is the probability that the mean exceeds 15. As long as we keep in mind that we're talking about a mean observation, the drawing looks the same, right? The mean is still centered on the mean, right, 12, and the standard deviation is 4, but because we're talking about a mean observation, we have to use our standard error, sigma over root n. So we've got Z is x bar minus mu over sigma over root n. Because we know how to solve these problems, right, from the test, from the assignment, and so we know how to solve these. We need to calculate a z-score, and then we need to use the z-table to find the area to the left, and then we can find the area to the right. And so we've got an x bar of 15. How far is 15 from 12? If sigma is 4 and the standard deviation sigma is 4 and the sample size is 10. Right? Because we've got 10 pallets. So we've got 15 minus 12, okay. 3 over 10 square rooted. Let's make sure I key this in right. Times 4. I get 3 over 1.264911064. Maybe someone check my work. So overall, I get 2.37170824. Is that what you guys are getting? Yeah, good. Z, because we know our Z table only takes 2 decimal places, right? We have to round Z properly to 2 decimal places. So Z is going to be approximately 2.37. So now, if you don't have a formula sheet, I've got extras far up here. Or if you didn't get one, you can have one. So 2.37. So I'm just going to write out what I'm doing here, kind of showing my work. So using the Z table, we find the area to the left of Z equal to 2.37 is, because remember, the Z table only gives you the area to the left. So we'll start there, and if we need the area to the right, we'll find it. So 2.37, I get 0.9911. Is that right? So the area to the right is 1 minus 0.9911. .0089. So what we can say then, right, is that the probability that this shipment will be overweight, right, over the 150 kilos is 0.0089, which I think is pretty good. That's a pretty good probability. It's low, making it good. Therefore, the probability that the shipment is overweight is 0.0089. I guess I better add another page here. Oops. B. What is the mean weight of the heaviest 10% of boxes? Sounds familiar. So the weights are centered on, is it 12? Yeah, sigma's 4. And we want the heaviest 10% of boxes. Right. Well, the mean weight. Okay. So if we've got the heaviest 0.1 in the upper tail, right, what we've got down here is we've got the lightest 90% of boxes, right? So that same value cuts off the lowest 90 from the top 10. And so what we're going to do is we're going to find the table entry closest to 0.9, right? And so keeping our wits about us, because sometimes things are not as they appear. 0.9 minus, so I'm landing between 0.8997 and 0.9015. So 0.9 minus 0.8997, just to see how far it is away. You see it's, I don't know, in my mind, it's 3 away, 0.0003. And so looking at the other one, it's 15 away. And so that's how I pick the closest one, right? But you can just use your calculator to see which one's closest. And so using the Z table, we find the table entry. Remember, the table entries are the values in the body of the table. We find the table entry closest to 0.90 is 0.8997. So now we're going to use that to find the corresponding Z score, which corresponds to a Z of 1.28. So we all know this section is a bit of review from the test that we just did, right? So nothing's really changing. The methods all stay the same. It's just that we're talking about a mean now. Okay. And so Z is x bar minus mu over sigma over root n. So Z is 1.28. We're trying to find x bar minus mu, which is 12, over sigma, which is 4, over the square root of n, which was 10. We get x bar minus 12 over 1.2649110064. You don't have to show that step. It's just in case you're checking my math, which you should be doing. So then multiply both sides by 1.2649 whatever times 1.28. 1.619086162 is x bar minus 12. So plus 12, we get x bar is 13.619086616. Therefore, the heaviest 10% of boxes weigh more than 13.62 kilos, let's say. Yeah. Okay. I guess I should throw in on average, just to emphasize that this is a mean weight. Okay. Any questions about that one? What you could have done if you wanted to, right, in finding this Z of 1.28, what you could have said is, well, if I want the 0.1 here, instead of using the 0.9, I don't really see the point, but if you want, then you could say, well, if I find 0.1, then that's just going to be the negative version of the Z that I need, right? Just keeping in mind that it's symmetric. So you could just say, using the Z table, we find the table entry closest to 0.1 is, well, yeah, 1 minus this, which corresponds to negative 1.8 or 1.28. And so Z must be 1.28. As long as you recognize that you need that positive value because you're above the mean, then it doesn't matter how you got it. Any questions about that one? C. What mean weights capture the central 90% of boxes? Well, it's all the same, but different. What mean weights capture the central 90% of boxes? So now, we have to find some x lower and some x upper, where this area, we're forcing it to be 0.9. Gotta add another page. So what we're gonna do, right, is we know, okay, so 0.9's in the center, and so there's 0.1 left over, split evenly amongst the two tails. And so we've got 0.05 and 0.05. And just as a check, those all have to add up to 1, right? So 0.05 plus 0.9 plus 0.05 is 1. Right? So what we can do is we can find the z-score for 0.05, right, with the table entry of 0.05. And then by symmetry, the x upper is going to have the same z-score, but positive. Right? So 0.05, I think that's the one that's split between, or evenly between two. Where are we here? 0.05. Here. Using the Z table, we find the table entry closest to 0.05 is, here's one of those where we land evenly between two, so it's either 0.0505 or 0.0495. I will use 0.0505. It's just the first one, which corresponds to Z of negative 1.64. Which is the standardized value of x lower by symmetry, z equal to 1.64, so the positive is the standardized value of x upper. We introduce it later, but what I want to show you guys is if you're looking for a central value, or the values that capture the central some percentage, 90%, 95%, whatever, what you can do, so this is all fine, you can do that, or if you flip to your table C, which is called the t-table. We haven't looked at this before, but if you have your, I guess I'll pull it up here. So your t-table looks like this. And what you'll see is you have these percentages up at the top. And those are going to be the central percentages. And so you can ignore everything in here. Those are all T's. Okay. But then if you go way down to the bottom, you've got this Z star line. So this is just your Z line. And what you can do, if you wanted to, if you want to capture, so you want the Z's that capture the central 90%, then you can just follow it down, and you find the Z of 1.645, which sounds reasonable, right? Because we've got our Z of, we always find ourselves between 1.64 and 1.65. And so here the table is just saying, okay, well, if you want the central 90%, it's captured between Z of negative 1.645 and 1.645. So that's something that we'll use later on, but because we're doing kind of a similar problem, figured I'd show it to you. Or using table C, the T table with a confidence level of 90%, which I'll just put in brackets as the central 90%. We find Z star is 1.645. So we can use that. Now, because we have so many options, right, we could have had, using the Z table, we could have had 1.64 or 1.65, and now we have 1.645. So for this example, I'm going to just use 1.64, or just stick to what we know. But I figured I'd introduce it here, the 1.645, because it is something that we will be using a lot. So for this example, I will use Z is plus minus 1.64. You could have used any one of those. It would be fine. So we've got Z as X bar lower minus mu. I'll start with the lower over sigma over root n. So the Z for the lower is negative 1.64 is X bar lower minus 12 over 4 over the square root of 10. Should have just, oops. Let's store that. So I've got negative 1.64 is X bar lower minus 12 over 1.2649 110, only 64 times 1.64 negative. So I get negative 2.074454145 is X bar lower minus 12, so plus 12. So the mean on the lower end, capturing the central 90%, is 9.925545855. Doing the same thing for X bar upper. X bar upper minus mu over sigma over root n. 1.64 is X bar upper minus 12 over 4 over root 10. Another page. 1.64 is x bar upper minus 12 over 1.264911064 times 1.64, 2.074454145. X bar upper minus 12. So x bar upper must be plus 12. 14.0744541. Therefore, the central 90% of mean weights is between, let's say, 9.93 kilos and 14.07 kilos. Nice. Any questions about that one? Okay. So, no more questions there, so I'll just let you guys finish jotting that down. So what I said before was that even if it doesn't say that something follows a normal distribution, we can still assume that it does. And what I'm introducing there is the central limit theorem. And so the central limit theorem says that if you're talking about a mean, as long as the sample size is large enough, right, the mean will follow a normal distribution regardless of where you took this mean from. Okay? So that's kind of a cool concept. So if you're talking about a mean, right, so an average, it actually doesn't matter where you sampled from, whether it's skewed or whether it follows a normal distribution, because by the central limit theorem, the distribution of any mean will follow a normal distribution. So that's kind of a cool, weird concept. Right? And so that's what we're introducing here. Of course, it hinges on some things, right? And so depending on how closely you want your sampling distribution to look like a normal distribution, then you'll have to collect large samples, right, to make that happen. Just to ensure that in case you're sampling from a skewed distribution, then as long as you have a large enough sample size, the mean will follow a normal distribution. And so if the distribution that you're sampling from, right, so a lot of distributions already follow a normal distribution, right? Heights, speeds, all these things that we could talk about, right? They follow a normal distribution usually. And so sampling from those and talking about the mean of those, we don't have to have a large sample in order for the mean to follow a normal distribution. Okay? So jury's kind of out. So in practice, some statisticians say a sample size of 30 is large enough, assuming that you're sampling from something that's roughly bell-shaped, right? So approximately normal, doesn't have to be exactly normal. And then others recommend a sample size of at least 40. I've seen people push for 15. 15's enough. Well, not really, but if that's all you have, that's all you have, right? And so it hinges on, right, so if the original population that you're sampling from, right, is not normal, then you need to have lots in your sample, right? You have to have a large sample size in order for it to stabilize. And so that's why you've probably heard, right? Oh, you have to collect a large sample, you need large sample sizes, and that's just because we need the central limit theorem to kick in, right? So we need the mean to follow a normal distribution for us to be able to do anything with it. So I've got this illustration, which kind of got chopped up by our example. But what I've done, just to show you how it behaves, is let's just for a second pretend that this is the population that we're sampling from. Right? Because, and I've got it in the blurb, there's 1,000 points in here. Because the sample size is so large and it's still showing that skew, right? Then this is from a skew distribution. All I did in R was I just generated a random from a beta distribution, which is skewed. Okay. So we've got this skewed population, we'll call it, right? Just that we're sampling from. And so what we're going to do is we're just going to take one guy, calculate the average of that guy, right? And so looks like it's way up there. And then we keep that guy that we've sampled already, and we pick out another one. And so now we've got a sample size of not 1, but 2. Right? So now we calculate the average. That counts the average down to here. Right? Then we collected another one, and we calculated the average of these 3 points now. And so now it jumped up a little bit. Right? And so, and then we took out another point, 4 points, calculated the average. And so here what we're doing is we're constantly calculating the average, and it's going to jump up and down, up and down, up and down. Okay. But what you'll see is that eventually it starts to stabilize. Right? So here we're drawing from a very skewed distribution. And so for it to normalize here or kind of stabilize around, so here this dotted line is the population mean. So here we had to hit like a sample size of 600 for it to be basically bang on, right? But even something starting here at like 200, it started to stabilize a little bit. Right? And so even drawing from a skew distribution, right, the distribution of the mean, right, will start to stabilize around the population mean, even at sample sizes of 200, right? Definitely at 600. Right? So there, the 30, right, the minimum sample size of 30-ish doesn't really apply, right, because we're drawing from a very skewed distribution. Questions about that? So it's just to show the central limit theorem at work. So there's a couple of things that we want to check, right? So are the sample observations, are they independent, right? And so in your sample, you want to make sure that everyone in your sample is independent of everyone else. Right? So you do that by random sampling, right? That's the best way to ensure that all your observations are independent. So as a rule, you want to make sure that your sample size is large enough, right? So n has to be greater than or roughly equal to 30. We'll push it to maybe 20 sometimes, right? But as a rule, you have to have a large enough sample size. And then the population distribution is not strongly skewed. We don't know that. We can't check the population that we're sampling from, so you just have to assume. And of course, as we increase our sample size, if we have a huge sample size, right, of 1,000, then we can be very lenient with each of these conditions because it will follow normal distribution. What we're doing for goodness. Any questions? So, no questions. Let's just start hypothesis testing. And like I said, so in this section, we're basically just going to lay out all the rules, all the, I don't know, the ins and outs, right, of everything that we have to do. But then once we've established that, then we can go on and we can say, okay, now we've got this type of problem, but the procedure for hypothesis testing stays the same. And so hypothesis testing, you probably, I don't know, at some point, I think I remember in science, whatever, you had to state your hypothesis. If I boil water, it'll turn into gas. That's my hypothesis. And then I tested and it happened, right? And so we've got some theory, some hypothesis that we want to test or prove. For example, right, so let's say we've developed this new pharmaceutical, shouldn't say drug, pharmaceutical, right? So I've developed this new painkiller, and I want to be able to say that my painkiller is significantly better than everything else on the market, right? So maybe in terms of how quickly it kicks in, right? So it kicks in faster than any other painkiller on the market. So what you're going to do, right, is you're going to take a sample of how long it takes for your drug to kick in, and then compare it to how long it takes other drugs to kick in. And so when we're able to say something like, it's significantly better than this other drug, that's where we need hypothesis testing. And so hypothesis testing is kind of the money maker in statistics. That's why you have to take this course or are encouraged to take this course, is just because hypothesis testing is everywhere, right? Whether you're in any of the sciences or business or even arts, right? So you put out surveys and you want to know if this group is significantly different from that other group, right? And so hypothesis testing is everywhere. And so we use it to establish just, is there a difference between my sample and the hypothesized value? There's going to be 4 steps that we follow for any hypothesis test that we do. Okay? And so the first step is you're going to state the null and alternative hypothesis. We don't know what that means yet, but that's the first step. Step 2 is going to be do the test. Do the test is really just calculate how far is your sample mean, let's say, from your hypothesized mean. How far is your sample mean from your hypothesized mean? So doing the test, all we've seen so far is a z-score, right? But a z-score tells us how far is x bar from mu, taking into account the spread, right? And if you have a glance at your formula sheet, right, you've got in section 4.2, you've got your z-score, right, that we just established. And then in 5.1, we calculate a t, but it looks about the same. And then in 5.2, we calculate another t. And in 5.3, we calculate another t. And so these all kind of behave the same way. But in the grand scheme of things, we just want to see how far is our sample information from our hypothesized information. And in step 3, we're going to find the p-value. The p-value is just going to be the area in the tail. Okay, so just kind of short notes here. It's the area in the tail. So far we know how to do steps 2 and 3 really well, right? We know how to calculate a z-score, and we know how to find the area in the tail, right? Regardless of which side of the curve we're on, right? The area in the tail is the p-value. And then step 4 is our conclusion, and our conclusion is going to has 3 steps in it. So in these subsections, I've just gone through and just talked about each of these steps, everything that you might need to know about each of these steps. And so step 1 was state the null and alternative hypothesis. And so the null hypothesis we denote by H subscript 0 or H naught. So anything subscript 0, we just say naught, so H naught. Oh, I have it here. H sub 0 is read H naught or H null, so the null hypothesis. H for hypothesis, of course. So your null hypothesis is going to be your hypothesis if everything stays the same, right? And so let's see here. So for that reason, you always have an equal sign in your null hypothesis. So your null hypothesis is that, talking about the drug example, right, is that my drug is the same as all the other drugs. Right? That's where I have to start, right, until I have proof otherwise. It's kind of like innocent until proven guilty, right? So we have to assume that these two things are the same until we have proof otherwise. And so usually what we want to try to show is the alternative hypothesis. Right? Sometimes it's not, it depends on the scenario. But the alternative hypothesis is, well, okay, if this isn't true, what do you think will happen? Right? Is mu not equal to this hypothesized mean? And so in this course, we're going to talk about hypothesis testing for means and for proportions later on. You can do hypothesis testing for just about anything, but for this course, we talk about the means and for proportions. Means are for numerical data, and proportions are for categorical data. So in this kind of first section, right, we want to talk about our population mean, right? We've calculated a sample mean, and we want to infer something about the population mean, right? And so our hypotheses will always be about the parameter, right? And so let me just highlight that. So in terms of the parameter that you're interested in, huge highlighter. So you don't want to hypothesize things about X bar or anything like that, right? You want to hypothesize about, okay, well, what does the population mean look like? Right? Or what does the population proportion look like later on? And so in our case, just to start out, you've got H naught is mu is equal to mu naught, which is just your hypothesized mean. Mu naught is your hypothesized mean. Hypothesized So if you have a look through your formula sheet, section 4.2, you've got your hypothesis test about mu, and then 5.1, again, the hypothesis actually stays the same. So nothing really changes between 4.2 and 5.1. And then 5.2, it changes slightly, right? I'm talking about mu diff, but your null and alternative hypothesis for the first little bit is always just going to be that mu is equal to this number. And so a key thing to keep in mind is that we do all this testing assuming that the null hypothesis is true. And so what that means is that if the null hypothesis is true, what we're assuming is that mu is equal to mu sub 0. So in our calculation for z, right, z is x bar, our sample mean, minus mu. What we're really saying, okay, if mu is equal to mu sub 0, our z score is going to be x bar minus mu sub 0, mu naught. So here, so z is x bar minus mu over sigma over root n. And since h naught is that mu is equal to mu sub 0, we have z is x bar minus mu sub 0 over sigma over root n. And that's the one on your formula sheet. So because we assume that the null hypothesis is true, that's what makes this mu change to mu sub 0, mu naught. Which, fair enough, we want to know how far is our sample mean from our hypothesized mean, taking into account the spread. And so in our alternative hypothesis, I'll just scroll a bit here. We've got, okay, well, the alternative, if mu isn't equal to mu naught, the alternative would be that mu is not equal to mu naught, right? So you tried this, you found evidence against it, so then you can conclude, well, then mu must not be equal to mu naught. You've actually got 3 options there, but the default is going to be not equal to. So you just say, okay, I hypothesize that they're the same, or they're just not equal to each other. Right? Or you could say, if the question said, what's the, something like keywords being less than, right? So is my drug time, or the time that my drug takes to kick in, is it significantly less than the other drug? Right? Then you would use the less than in there, just because you have some idea about what might happen. And so you've got less than, or you can use greater than, or not equal to, which is just going to come from the question. So, any questions? No? So you've got those notes. Maybe flip through them over the break. I don't know. But otherwise, have a good break, and I'll see you on the other side. Yeah. And I think everyone got their test back, yeah? Cool. Cool, cool, cool. Now it's all yours.